So in this example, this is going to be a diverging lens example, and it's not going to be such a straightforward application of the object image distance equation. Okay, there's going to be a little bit of convolution, if you will, but we'll talk it out. So let's read the question. So we have a beam of parallel rays that spread out after passing through a diverging lens, as they would. Okay, that's what rays do. When they pass through a diverging lens, they spread out on the other side. They spread out on the other side as if the rays all came from a point 20 centimeters from the center of the lens. Okay, so that's an important value, this 20 centimeters. What is it? Well, the way that diverging lenses work is, let's look at the purple ray here. Purple ray, let me use purple marker. Okay, this is the object, and these are all the possible light rays, or there's an infinite number of light rays that can come from the top of the object, but we're going to pick three principal ones, okay? The first one is going to go parallel to the optic axis, and then when it meets the diverging lens, it's going to diverge out, okay? And this angle here, this divergence kind of angle, is the angle that would be made if that light was instead of coming from here, and if it came from the focal point, okay? So with that being said, this 20 centimeters here, this is going to be F2, okay? So what sentence number 1 is describing is principal ray number 1, okay? Which tells you the focal point of this lens. And so now we have the focal point of this diverging lens, but we need to apply our sign rules. And our sign rules for diverging lenses is that, and if we look at that summary in the back of the book, the sign rules defined with respect to the outgoing side, okay? So if the radius of curvature is on the outgoing side, then R and F are positive. But if the radius of curvature on the incoming side, F and R are negative. And sure enough, take a look at the first, right? This radius of curvature right here that creates that first lens. Boom. There's our F and our R. Okay, well, R is 2F, but just pretend, right? There it is. It's on the incoming side. Right, this is the outgoing side, right? There he goes, out into the world. All right, ray number 1, out into the world. This is the incoming side. Let me see if I still have that pasted here. No. If it's not on the outgoing side, then the radius of curvature and the focal length are negative, okay? And therefore, R is on the incoming side, so the radius and the focal point are negative. So that means our F is negative 20 centimeters. All right. And so now let's continue reading the problem. You want to use this lens to form an erect virtual image. So erect is another way to say upright. Okay. And that is 1/3 the height of the object. Okay. So we're basically a magnification of 1/3. All right, so with a magnification of 1/3, and remember the magnification is equal to negative S prime over S, Y prime over Y. Where should we place the object? Where will the image be? Okay, so basically we're given F, and then we're given a relationship between the object and image distance or the object and image height. So see, we're kind of like given everything in a convoluted way is what I'm saying. But we're still going to apply the same old equations, object image relationship. Okay, but we don't really have anything to plug in directly for S prime and S, but we do have a relationship to plug in. So let's spell out that relationship. That relationship comes from this right here. The relationship is that, let's say, how about S over 3 equals negative S prime, or what we could do is S equals negative 3S prime. Let's do that so we can avoid, putting fractions in fractions, okay? Let's use this relationship, and that's going to allow us to get rid of one unknown and have this object image equation in terms of only one unknown. So our 1 over f is 1 over 20 centimeters negative. And then we're going to replace s with negative 3s prime. And now we're going to solve for s prime. So what's the easiest way to do this? We could just do 3 here. So 3 minus 1 over 3s prime. Right? 1/2 minus 1/3 is 2/3. Yep. So now we can solve for s prime. So s prime is going to be negative 3 over 2 times 20 centimeters. That's 1 over s prime technically. Let's just do it in baby steps, right? Yeah, so 1 over s prime, we bring the 3 on top, 2 on the bottom, times 20. Okay, great. That comes out to be negative 3 over 40. And then we inverse that to get s. So that becomes, and then s prime is going to end up being negative 1 over that, 13.33. Okay, so where should the object be placed? Well, now that we know the image distance and we know the magnification should be 1/3, we can figure out what the object distance should be. So if we want to find the object distance s, we're going to use m and then our knowledge of, I'll use m and s prime. So we know that m should be 1/3, and that's going to equal negative s prime over s. And so now that we know what s prime is, we can solve. And s is going to be, s will equal 3 times 13.33. About 40 centimeters. Okay. Where should the object be placed? 40 centimeters to the left of the diverging lens. And where will the image be? Well, the image will be also on the left. Why? Because the image location is negative, and that's on the virtual side of the lens. And the virtual side of the lens is the left side. Why? Because we expect images to be on the other side, right? The real side of the lens is the side where we expect the image to be. So the virtual side is like on the side that is basically the incoming side of the ray. So it's a virtual side, negative 13.33. So that's where the image will end up. So that answers the second part. This answers the first part. Part B is to draw the principal ray diagram, and that's where this this picture comes into play. This is the principal ray diagram. You draw the 3 principal rays. The first one is parallel to the optic axis. Okay, the second one, which is the green guy, goes from the top of the object straight through the center of the lens. And then the third one goes from the top of the object to the focal point at the other side. And then it ends up being parallel to the diverging lens. I don't have orange on here. Okay, so once it hits the lens, then you draw it parallel to the optic axis of the diverging lens. But I'm not going to ask you to draw any rays or anything in the exam. Okay, so just focus on the math part. Where the ray diagram comes in is just helping you understand all the cases, right? What kind of image do you get when the object is inside the focal point? What kind of image do you get when the object is outside the focal point? What kind of image do you get when the object is at the focal point? Okay, the ray diagrams are to help you characterize the different characteristics of the image depending on where the object is placed in reference to the focal point. So that's the diverging lens example I wanted to do. I might do one more. We'll go head over to the other lecture PDFs, and there might be a good diverging lens example there as well.